Morning all, and welcome to this invited talk session. My name is Michelle Wieland. I'm from EPCC, the University of Edinburgh, and I'm here to chair this session. So our first speaker is Dr. Nils Wedi. Dr. Wedi obtained his PhD from the Ludwig Maximilian University of Munich in Germany, and his 27 career at the European Centre for Medium-Range Weather Forecast encapsulated a diverse range of both technical and scientific work. He's a digital technology lead for Destination Earth at ECMWF, a recent initiative which brings together the European Commission's Green Deal and the digital strategy. Destination Earth will create a high-precision digital model of the Earth system to model, monitor, and simulate natural phenomena and related human activities. Prior to his appointment, Dr. Wedi led ECMWF's Earth System Modeling section. He actively collaborates with researchers worldwide, in particular through his role as a co-chair in the World Meteorological Organization Working Group on Numerical Experimentation, which represents a key link between weather and climate research. Please join me in welcoming Dr. Nils Wedi to the stage.
Right, thank you very much for joining me this early in the morning. And I'm looking forward to tell you a little bit more about nothing less than digital twins of our Earth system. And this is really the essence of this program called Destination Earth. And it's something that is funded by the European Union. It's an ambitious program that's trying to combine the goals of the European Green Deal, carbon-free society, energy management of renewable energy, and so on, with the digital strategy of Europe, which you already have heard a lot about in this conference, and I will talk a little bit more about that during my talk as well. And so let's start. Of course, I would like to acknowledge my co-authors. During the course of the presentation, you will see a lot of other names because this is, of course, a collaborative effort with many people, many countries across Europe and worldwide. And I hope you see the reflection of that during my talk. So just to give you a bit of background where ECMWF, which is the organization I work for, the European Weather Center for Medium-Range Weather Forecast. And this is a little bit the history that you see here with respect to how we evolved over time. So right at the beginning, I think we had one of these machines that is also exposed here in the exhibition, which is the Cray 1. I think we had serial number 9, which is right at the bottom of this graph. It was setting us up for the first operational weather forecasts at ECMWF at a time when people thought medium-range weather forecasting isn't really possible. And I think we're at a similar sort of venture now where we are saying we're going to do digital twins of our Earth system, and clearly a lot of people think, well, that's probably not possible. But you can see that our progress has been very closely associated, as also described in this paper, with Thomas Schultes and co-authors, where we had a gradual increase, of course, of computing power over time, but at the same time, you see that we were able to increase our horizontal resolutions of this time in numerical medium-range weather prediction. And roughly, actually, we double resolution, horizontal resolution, the horizontal grid spacing between the grid points on the globe every 8 years. And we are trying to reach something like this goal of 1 kilometer global resolution by the end of the decade. But maybe, with new technologies, the things that are presented at this conference, we can achieve this even earlier, because clearly the weather and climate problem, the weather in a changing climate, is a pressing problem that drives us to try and achieve this earlier than this roadmap. And you can see, of course, that it's also closely associated with Moore's law. So digital twins. A lot of people have a lot of expectations what these digital twins really mean. But it's not a new idea. It's, of course, something that's in medical sciences, the idea of being able to have a heart and play with it before you do it on the real thing seems a natural idea everyone can commit to. But also on the technical side, aeroplanes and so on, and it's a very common place to also augment, and this is important, augment our knowledge that we have from experiments with numerical digital technology. And the same we want to do for weather and climate science, where we can, we only have one Earth, and obviously we want to be able to explore as much as possible what are the possible scenarios where we're heading, basically, on this planet. And so the depiction here of Antarctica, almost like a heart, actually, is not by chance. So digital twins are really much more than a data mapping exercise, and I hope I can convince you of this during the course of this talk. This is beyond computer games. Now there are a number of companies that are also present at this conference that clearly, as you can see, are also using this information. Of course, as we are providing more easily accessible information about the real weather, it can, of course, be also used in Microsoft Flight Simulator, and I think they're doing an excellent job. But as was mentioned here, for example, by, I think, the COO of Black Shark AI, it is more than that, and we have many more opportunities when we have a real-time digital twin of our planet that goes really beyond, say, the Google Earth that we all appreciate and the Apple Maps and so on. And so NVIDIA, for example, has a big vision here with building Earth 2, a supercomputer combined with massive machine learning capabilities in order to help accelerate on our path of being able to explore what is really possible to manage our Earth system with machine learning technologies. And it's also, of course, how you bring it to the user, how you make it more realistic, how people can imagine, because climate change is measured at the local scale, and therefore, it is also experienced at the local scale. So obviously, you have to bring it to the user, and you have to make it real. What is there that I'm going to experience at my house and whatever in the future? So here, Omniverse is like one example where GPU acceleration, for example, can help to sort of bring this vision closer to the user, and this was driven by the 1 kilometer input data that we produced when we ran like a 1 kilometer global simulation on the Summit supercomputer here in the US. So this is just one example of where we are today. You see two pictures. One is real, one is from digital twin data at 1 kilometer resolution. So you take a guess which one is the model. So this, I take it away for you. This one is the observed satellite picture. It's just really a random sort of snapshot of what we can do today. And on the right-hand side, you see the Artitov emphasis. So what this is really, we're translating the information from our digital twin, our 1 kilometer digital twin, into the observed space of the satellite instrument. It's like a full 3D observation operator that recomputes, if you like, what the satellite would see. And we're getting pretty close, I would say. This is also work that was produced on the Summit supercomputer, and I would like to especially acknowledge again, of course, all the people involved, like Ina, Polichuk, Ion, he's just sitting here, can answer all the questions later. And so I think it's a great effort that we got this to run and that we could sort of translate this basically into these pictures. And you can really zoom into these pictures. I can't do it right now because we're still working on the visualization procedures, but you could zoom in right there. There's a lot of detail there. And I think we're getting pretty close. Of course, there were challenges as well, which I will talk about later. But once more, thank you very much, DOE, and thank you much to the InSight program, which has been fantastic for us to enable these kind of flagship simulations. So the next thing, of course, is we want to go beyond these pretty pictures, right? We need to quantify uncertainty. This is a really important point, and sometimes a bit overlooked also with leadership facilities, both in Europe and the US, because we need to reach also statistical significance of our results, and this typically means running like ensemble members perturbed by initial conditions and perturbed by along the model trajectories. So here you see an example where we actually, this is not a movie in time, but it's a movie overlaying 50 different realizations of different forecasts perturbed to give you a span of this particular situation where I think there was a lineup of 5 hurricanes coming towards the United States. And this is also the next operational system we will have at ECMWF. We will be running 50 of these ensemble members at this kind of spatial resolution of 9 kilometers next year, every day, or in fact twice a day on our new machine. So this brings us then to this Destination Earth initiative that I was mentioning already. It's funded by the European Union, as I said. It's managed by the entrusted entities, ECMWF, that's our organization, the European Space Agency, and EUMETSAT, who operates a number of satellites for ESA and also their own. The key elements of this Destination Earth is, for once, the digital twin engine. I will talk more about what that really means, but you can think of something like a gaming engine, development platform environment where essential tools will be available to build digital twins. The digital twins themselves, so the first two that we will implement, one is on extreme weather events and the other one will be on climate adaptation. And then a data lake. So data lake is something that many people talk about, and maybe some are not quite sure what it is, but it's a virtual organization of different data sources, because Destination Earth and digital twins are also about fusing information from different disciplines and bringing this data together. So there's a lot of work going on standardizing, on kind of trying to bring together these different data sources in order to make new information that we didn't realize before. And then there's the core service platform, because you obviously want to interact with the users. We want to give users the space to be able to explore this data. This also means computing resources as well as access tools, templates that you can copy and use for your own. So maybe somebody in a climate domain has good templates, how to access data, how to bring it into their application. Well, I can copy this, and because I'm from the health environment, and I could use actually exactly the same workflow, but bring it and use it in my own environment. So these are the ambitious goals. The timeline is very short. In fact, we need to deliver this already in 2.5 years. Now, we shall see how far we get. But of course, this is a larger program which is set in different phases, and we're already discussing like phase 2 now from the European Union, and hope that over the next 10 years, this will transition into an operational environment. All of this is built on the large investment of the Euro-HPC, the joint undertaking, which has invested 8 billion towards exascale computing resources. And we will be using the resources from the LUMI computer in Finland, Leonardo in Italy, and Mare Nostrum 5 in Barcelona. And I encourage you, of course, to see those booths here at the exhibition. They all display the great work there, and it's all based and we will basically make good use of all these platforms in Destination Earth. Because in fact, 10% of the Union's access, the funding model was such that the European Union contributed 50% and the countries contributed the other 50% for the funding of these computers. And 10% of this has been dedicated and approved dedicated now for strategic initiatives such as Destination Earth to make progress using these unprecedented computing resources in Europe. And there is, of course, more coming, and therefore we need to build actually workflows that are kind of resilient so that we, and sort of reproducible also on the machines that are emerging in the future. We get a big exascale computer in Jülich to come, and also there are the Alps machine that you've heard talks about already, which are exciting avenues where these workflows can operate as well. One other thing I maybe wanted to mention as well, because I'm also involved in the World Meteorological Organization, and they recently showed a graph that all the computing power, of course, is reserved, if you like, to the Northern Hemisphere, because like there's the US and Asia and Europe that invest a lot in computing power. There's hardly anything in the Southern Hemisphere. So about the workflows that I will talk about in a minute, really I think we need to also more distribution of computing resources in order to make a vision happen where you can bring this information to all parts of the world, especially in the sort of problematic of climate adaptation and so on that I mentioned before. And it seems obvious to me, at least, that some of this climate financing that was discussed recently at the COP27 could be used to also employ it on computing resources that could be hosted locally in the Southern Hemisphere. Because if you think about the funding kind of model and idea, it seems a no-brainer to me that this would be a good opportunity also for HPC. But continuing on the story here with respect to Destination Earth, so this is about the digital twin Earth. Towards it, we are responsible particularly for creating this digital twin engine capabilities that I mentioned earlier. The Extremes digital twin will be implemented. And we're working with the French Meteorological Service, Météo France, and partners from 22 European countries to enable actually a configurable capability for interactive European monitoring and prediction at city scale and down to for meteorological, hydrological, and air quality extremes and applications. And this will be running on the Leonardo supercomputer. There's then the second part, the climate change adaptation digital twin. It will also provide capabilities and service in support of climate change adaptation for policies, also in mitigation scenarios. This is led by CSC, the supercomputing center in Finland. It will lead an international partnership on this program, and you can find out more at this particular website. But in particular, we will be implementing 2 storm and eddy resolving Earth system models deployed on these supercomputers. One of them is the IFS. It's called here in America sometimes the European model. And the other one will be the ICON model from the German Weather Service that is developed in collaboration with the Max Planck Institute in Hamburg. And so there will be also a number of countries involved in these initiatives in order to develop this, and I also encourage you, of course, to visit the corresponding centers at their booths today. We are also engaging with ATOS, and we have launched with them a center of excellence in weather and climate modeling. And as our director here said, I think very well, it brings together, if you like, this world-class expertise in the computing side, the computational science side, but also the Earth system side, our side, to advance basically this for medium-range weather forecasting, but really in destination Earth, it is also about advancing how we bring the data to the users, advancing how we can use these machines that are now emerging with their changing technologies. And as you can see here, the focus of this is very much also heterogeneous computing, data-centric workflows, machine learning, and information exchange on quantum computing, which arguably, from my perspective at least, is still a little bit further away for weather and climate prediction. So one of the vehicles we use in order to engage with vendors, in order to make this sort of a reality, is our weather and climate dwarfs. It was inspired by this nice idea of the Berkeley dwarfs that were developed here in the US. And they are verifiable collaborative tools for vendors and academia that we explore, where we work with them to optimize basically key elements of our forecasting system, key elements of these digital twins, to accelerate them for the platforms on which we want to run them in the future. And there are just some examples here. For example, one of the big things in weather and climate models are the parameterizations, like think about the microphysics interactions in clouds, or think about radiation. Those things need to obviously run very fast. We have other algorithms like the spectral transforms, which is a combination of FFTs and very large-scale matrix multiplies, which clearly can be optimized very well on different computing platforms. And there's also the more newer efforts to try and use DSLs, like source-to-source translation of our parts of our code, in order to translate optimized kernels and at the same time stay portable with your overall computing environment. So these are just some examples of this collaboration. But it's clear, in order to implement digital twins, there are extreme computing challenges. They are on the technology side and on the science side, and this is just sort of expressed also in this paper here about the digital revolution of Earth system science. And some of the solutions we are thinking, of course, is not just a single solution path. You know, it's work on the numerical algorithms, the methods, it's work on machine learning, it's working on programming models, it's working on heterogeneous processing, memory, interconnect technology, and how we can best exploit these functionalities. But as this recent article says, you know, could the world's mightiest computers be too complicated to use? And clearly we think not. But there was a discussion, I think, also at this conference, whether these supercomputers that we have today actually need to, you know, there was this mention about the use efficiency, I think, of 0.8% or something like this. So clearly we need to rethink how we can basically map these world problems like weather and climate onto these supercomputers. So we also have challenges on the science side, you know, it's clear, you know, we can present very nice pictures, but let's look under the hood, and then there are a lot of challenges still unresolved, and this is something that we need to work on, of course. So one, of course, is a modeling effort as well, which is a continuous effort of improving our models, making sure that our energy balances are right, making sure that we don't lose things, water and whatever kind of, you know, in some corners of the model. There is also the effort of observation information extraction, data assimilation, which is one of the big key elements that allows us today to have these fantastic pictures that you saw earlier. There is the element of integration, co-design with impact modeling, and I will come to this a little bit more further, but we really need to bring much closer, if you like, the user applications like hydrology. I mentioned energy management, especially when we rely more and more on renewable energy, how we bring this already into our digital twin environment more directly. There is the uncertainty that I already mentioned, how we measure uncertainty, how we can quantify uncertainty. And then the R2O, the process of bringing our research exploits into the operational environment and how we verify that these things are doing what we intended them to do. I mentioned this is all part of big partnerships. This is, of course, Destiny on the one side, which is basically providing the first implementation of this idea. But then there's all this, the WMO, the World Meteorological Organization, the World Climate Research Program, which successfully has produced multimodal information that is crucial and really underlying the IPCC reporting, which allowed us to already take action and be the fundament, if you like, of the discussions that we have at COP27. But also in Europe, we have this Copernicus program, which is already providing a monitoring of our Earth system in a very regular machinery, which is also provided by ECMWF for the part of the atmospheric monitoring, and a very popular data set we provide, the reanalysis, which uses the same forecasting and assimilation system, but for the past 50 years in order to have a very consistent data set of how our Earth system has evolved over this time scale. And of course, there's all the science, and in Europe, we have all these connectivity questions as well. How do you bring all these supercomputing centers that are distributed across the world together? How can we share information? How we can actually extract the information produced there and share it across a wider network, which is a very active discussion in Europe as well. So this brings us really to the end side then, to the, how we transform information from these more realistic global scale models to more realistic local scale, including the impacts that matter at the local scale. So better simulations is certainly one of the aim, more realistic kind of global models, combining observed and simulated information and supporting these actionable scenarios, which is really, we're going beyond the aspect of just, okay, we will have a global temperature rise of 1, 5, 2 degrees, right? But we want to know what it means for me locally. And this is really where the actionable scenarios come in. So then, of course, it has to be interactive and configurable as well. Now, it is clear to everybody at the moment that maybe not everybody in the world can run their own digital twin because of these computing resources that are involved in this. But we can invent plugins, invent basically things that can run alongside these sort of platforms that we have distributed across the world, where you can attach, if you like, information that is very specific to you and interesting. So there are a number of software ideas around how we can manage this with the resources that we have today. So I think that's something that we clearly want to exploit as some of this. And there are here just some examples, basically. For the river management is one. Here the Arctic amplification is an important aspect because we see that storms kind of break the ice. You get the leads, and the leads change how it interacts with the atmosphere. It changes the ice growth, and therefore, it can lead to much more rapid, if you like, decline of ice surfaces. And this is one of the issues that our models don't capture very well today. But it's crucially important, of course, for understanding what's happening to the Arctic environment. Changing landscapes is just one other example, because we continuously see our lakes shrinking. We see basically flooding, inundation areas, and how they interact perhaps with the local environment is something we don't know. It's really important also for the wetlands to understand the changing wetlands, because for the methane, and methane, of course, ultimately, again, a driver for the global heating. So these are just some examples. So this brings us to Earth system modeling complexity. And I just describe it here based on the complexity that we have in the European weather model. But this is quite true for all the modeling activities that we see in weather and climate. It's this really the adding of the new Earth system components. In our case, it's an ocean model, a wave model, an ice model. You have the land surface interactions with the vegetation, topography, the seasons that you need to describe well. You have the interaction with the CO2 and the water cycle, of course. You have, therefore, the lakes, coastal domains that you need to consider, and deeper down into the soil. So all of these processes are encapsulated in our digital twin. So just to give you an example where this is sort of heading, we had the reanalysis that I mentioned earlier. It had the resolution of about 80 kilometers. It was called ERA interim. Now we have ERA 5, the CS5, S2S timescale. That's sort of something like between weather and seasonal timescales. So in between is at 30 kilometers. Our ensemble system today is at 18 kilometers. As I said, next year will be at 9 kilometers as well. Our high-resolution forecast is at 9 kilometers, but Destination Earth is targeting the 1 to 4 kilometer resolution for all of this. And then I mentioned already the interaction, if you like, with the impact sector modeling and really more closely co-design with these user groups in order to make progress here. And also we see actually a stronger convergence between the weather community on the one hand and its operational procedures and the climate prediction systems that are emerging in the near future. So we want to exploit this, of course, in the context of implementing Destination Earth. So we have this classical axis really in Earth system modeling. You have the resolution aspect that I already mentioned. You want to have this increasing resolution. You have the space of the Earth observation, the data simulation. Clearly, we have also a growing factor there. And in fact, we want to better make use of these, because I give you an example. Today in operations at ECMWF, we have probably something like 500 million observations coming in, where we effectively, after quality control, making sure you remove basically all the errors and that, you end up with perhaps something like 50 million. So this, could be a lot improved if we had better ways of extracting the information. But it's, of course, multivariate information. So, you have overlaps. You have also information where you need to check which one of those that you are receiving has the best quality and how it impacts and the different parameters in your model, like temperature, moisture, winds, and so on. All of this, of course, is impacted by the computing resources that are available, and you also the complexity I already mentioned. Do you include an ocean, sea ice? Do you include special models of biogeochemistry? How do you include them? Can you actually observe them? Can you initialize them? These are all big questions. And of course, I mentioned the size of the ensembles and that you can afford in order to achieve statistical significance. But what is the new axis is also the application side. Because if you think of digital twins, of creating this data and streaming this data out, we need this many, many different applications that want to listen to this information and want to extract and digest this information. And that needs to be scalable as well. So, and that closely relates, of course, to the data strategy. What is our data plan for this? So today, this is roughly the numbers, 6.5 million points times 137 levels, say 10 prognostic variables. At 9 kilometers, it's about 9 billion points. Our production rate is probably a bit more than this now today, but say 150 terabytes a day. This is classical numerical weather prediction. I already showed you earlier on the slide, I didn't comment on it, but with this ensemble size of 50 members of these, clearly this grows dramatically more. But when you go to 1 kilometer resolution, you have like 256 million points, roughly 111, 10 prognostic variables at 1 kilometer, say. This is 352 billion points. And we anticipate production rates of 1 petabyte per day. Just sort of as a comparison, the human brain has about 80 to 100 billion neurons. So we're kind of exceeding that now, basically. So how do we do this then? We are thinking of a framework, really, of workflows for this, as I mentioned perhaps already before. HPC adaptation is one key element, of course, of all this. IOs and data workflows is another area of concentration. And then software management, controlling these workflows, cloud environments, how do we visualize, how do we connect with these, is another area. These are like the work packages that we have in Destination Earth. So think of a gaming engine type framework, but for Earth systems, a collection of APIs and services that we will create. These are opt-in initial components that create a portfolio for destinationers. So workflow managers, data structures, parallelization library, model plugin, and a number of these data cube APIs, visualization and rendering service. These are just some examples of these kind of portfolios that you can opt into to build, if you like, your own digital twin in the future. How does this map? So I don't know how well you can see this. So you have the HPC center, say the joint undertaking in our case. You have the digital twins that are simulating and observing production, can be run in either continuous or on-demand mode. Then you have the data streaming that comes out of these digital twins. It's a 4D resolution coupled with applications directly, perhaps already, water, food, energy on the fly. You have the aspect of machine learning. You may be able to even train and apply machine learning on the fly in this system. So this all happens still on the HPC, as you can see. Then you have also applications that can either operate immersively in these sort of data space, also on the HPC, but they could also be, of course, on what we think of associated, like not JU-funded, sectoral, if you like, edge computing data spaces that sit close to the production HPC centers. So this is what we call the data bridge, in fact, in Destination Earth. So this connects to our data lake. So the data lake could be, it's a virtual environment, of course, but it has also some really physical hardware components that can be distributed across. And, and then you have basically the scalability of this, because you can deploy at each of these supercomputing centers such a data bridge, so close to the data where we produce. So we anticipate to have at least the 3 data bridges at the 3 locations of Leonardo, Lumi, and Mare Nostrum 5. And then we connect them for the specific task of digital twin data across Europe. And of course, we want to intimately connect with these new approaches of machine learning, which is one aspect is perhaps the more straightforward one, is really just to increase the speed of the simulation, the data flows, and emulating data compression, data mining, data assimilation. But then we are targeting also the systematic errors in our system. Can we learn more about this by using machine learning? And can we employ this maybe also to improve our errors with respect to, and our uncertainties with respect to quantifying basically how well we capture the envelope of a certain weather and climate evolution? All of this is supported, of course, by this data flake portfolio, so which is, think of it as a machine-readable thing. Think of a user coming in and asking a particular question from his domain, but he may be not understanding all the complexity of weather and climate. He just asks, I need some sort of temperature. And then how we can translate this basically into what, what we have, and how can we best serve, if you like, that application with that temperature. So there needs to be a mechanism, almost like a service that kind of translates the wish into an actionable retrieval. So all of this could be supported by machine learning. And then, of course, the aspect of fusing with what I just mentioned with these different sectors of health, energy, transport, environmental protection, and extreme events. So this brings me to the end, really. So supporting global Earth system stewardship is one of the high goals of Destination Earth and digital twins. Novel investment in infrastructure and technology, as I mentioned, HPC adaptation, the workflows, orchestration, and visualization, to make it real, to make it understandable what climate change means for each individual. And then big data handling, of course, is clearly part of this. Ultimately, you translate 1 petabyte a day into a decision that's like 1 byte, yes or no. And so this is really how we need to manage this in the best possible way. And so embedded Earth system information is really what we want to feed into the wider digital environment to enable a creation of new information. You can create this new information. And that's all I have. Thank you.
Thank you very much, Nils. We have time for a few questions. If you want to ask questions in the room, please go to the microphones that are in the aisles, so halfway down. There's a question coming up right there. Yes, please go ahead.
Good morning, it's Nicolas Sardo, the Open Parallel from New Zealand. Nils, you promised a great presentation, you delivered. The question comes into integration and what I call the topological platform. If I'm going, for example, to design a digital twin in the southern hemisphere, but for a resolution lower than 1 kilometer, let's say 100 meters or even less, how would I integrate? Because you just say that there is not many resources in the southern hemisphere. So I'm trying to imagine the topology or the mathematical model where this thing will integrate in the next decades to come.
Yeah, so we have also what we call like on-demand regional focusing digital twins that connect to the Extremes digital twin. So if you wanted to do something like that, it would be like a similar mechanism. So you could design basically, and we are designing and preparing interfaces, for example, this polytope interface that will extract the boundary conditions from the global digital twin and make it ready so that you can actually plug it and use it in your, say, more regional application that you have. The data access for that is probably small or smaller. So that will already provide a dramatic data reduction. And there will be sandbox spaces available. And in principle, ultimately in destinations, we want to make them available not only to Europe, but to like, you know, a larger community. So there are computing resources, if you like, made available that can then use this. Now, if we think about investment with respect to the climate finance I mentioned earlier, what this means is there could be like core service platform type investment, for example, in attached to HPC, attached to kind of enough computing resources in the southern hemisphere that could link to our data spaces, that could link to the information that you require in order to drive your particular digital twin over New Zealand, for example.
Do we have a set of standards that we both agree on?
And that's something, standards is very much what we need to evolve ultimately in Destination Earth. There needs to be more discussion. The standards on how we feed, for example, these large I/O, so these large machine learning data pipelines. I don't think there are necessarily all these standards. We have well-defined standards in numerical weather prediction. You know, we have WMO formats, they are OGC approved. You know, like how we format and self-describe our data. Because ultimately we don't want to, of course, when I talked about the streaming, for example, we are streaming not files, we are streaming messages, information that basically is self-descriptive. So ECMWF has always run in an already object-indexed way so that you can ask for temperature over Europe. You know, you can ask like as a scientist, you don't ask like give me file A1570 or something like that, okay? So, and very much that we want to transport across these computing centers to make this accessible, but ultimately make this accessible in the wider digital environment. So you can ask exactly that.
Okay, so let's move on to a question from our online audience. It's a hard one, but climate modeling is now at an unprecedented level thanks to HPC, but so is climate change denial. How can we address this disconnect?
That's a tough question, you know, like, I mean, some deniers, as we know, are just deniers. They won't be convinced by anybody. We had a sort of joking a conversation last night where, you know, people that believe actually in the outputs that we produce with digital twins, like, you know, looking at the inundation map and the reoccurrence of flooding for a particular area, the climate understanding person will sell this house and the climate denier will buy this house. So, maybe that will convince them then when they flow away, or they won't have a house anymore.
Thanks for that. Let's go down this aisle here, straight down.
Thank you. So my name is Kees Laat, University of Amsterdam, and I'm also part of SciNet Network Research Exhibitions. So my question is, if you build these digital twins and you produce 1 petabyte a day, ultimately, do you have any idea what it would mean for the networks surrounding Jülich to get this data to clients that want parts of the data, and how you will get the big data flows in from your sensors around the world to check your 1 kilometer resolution? So what does it mean for the networks, and can we showcase that here on the show floor in the coming years?
Yeah, absolutely. I mean, data compression and data reduction is like absolute key in this whole thing. That's why we are coming, say, with this elaborate data management plan where, you know, the 1 petabyte per day is on the HPC. It's produced what we can, it's all the information. Now, the different applications will not all need that 1 petabyte. Everyone needs their slice of this. We need to parallelize basically the access and the information content that we can targetedly extract from this information. There will, think of it like a big observation, a digital observation. It continuously produces information. Not everyone needs everything from this observation. And also, if you're not listening to it, it might be gone at some point. So we are not preparing for archiving all these petabytes of data. We are preparing for this to continuously produce and reproduced. And then you listen to it and you capture and collect, if you like, for your field campaign what you need. And that will be already substantially less than this 1 petabyte. So in terms of networking, we are thinking an immediate reduction to the data bridge of like hundreds of terabytes. Hundreds of gigabytes. And then flowing out, actually, we are thinking of terabytes, perhaps only, ultimately, to core service platforms and so on. So there is a substantial, if you like, exponential reduction as you go further down the line. How exactly we will be able to achieve this for the particular use case is very much a topic of Destination Earth. It's working very closely with those application providers that have these specific wishes. And in fact, some they don't even know yet what they really want and need. And sometimes this has also led to, give me everything and then I sort of figure it out. But no, you can't just download everything and then figure it out. We need to sort of work with you to actually understand what do you really need. And I think that's part of Destination as well.
I would like to challenge you to not limit yourself. The networks can do way more than you think. And we should have these challenges here at Supercomputing and show them. Thank you.
Okay, thank you for the comment.
Okay, let's go for one more question from our online audience, and that is, how much are predictions impacted by events such as, say, solar events or the moon's gravity, and how are they accounted for in your models?
Well, obviously the sun and the radiation is input to our kind of like daily life, and that they are, you know, well reflected in the Earth system models that we have. But if it's about like sunspots and things like this is a minor effect basically on the, you know, overall evolution. And I don't think, well, scientific consensus, I would say, is that we don't account for this right now.
Okay, thank you.
Hello, good morning. Thank you for this presentation. I'm Philippe Segers from Genci and the Press in Europe. I would like to know a little bit more about how this Destinity Earth translate into your operational operation at ECMWF on numerical weather forecast. What can you use from what you learn on Destination Earth on data assimilation and on your future forecast and on the new resolution of your next forecast for operation data?
So the extremes digital twin will be fed in part by the data simulation that is performed at ECMWF, so, but at higher resolution than what we do operational. So it's kind of like a step ahead. So rather than like in the reanalysis where we're using a well-established operational system and use it for the past 50 years, in Destination Earth we're really using a system that is kind of like a few steps ahead of what ECMWF might use in operations in the longer term future. So it's very much exploring, if you like, the possibilities that we want to go towards.
But my question was on the other way. Our Destination Earth is useful for the numerical weather prediction.
It's immediately useful because we are using the same kind of models, you know, the Earth system model environment, and both actually at the regional level as well as at the global level are very much the same underlying tools that we also use in our daily operations. So it's the same code, if you like. It's the same model. Is that what you mean?
No, but well, data assimilation and data assimilation at these scales, we are not doing data assimilation at 1 kilometer scale so far.
Absolutely, but that's what I meant. Like part of Destination is exploring data assimilation at higher horizontal resolution. So we are experimenting with this actually right now. Of course, ultimately, we are facing the challenge, and we will probably initialize from coarser resolution data simulation in Destination as phase 1, because there aren't necessarily all these observations available at these local scales. So the models make up basically the dynamic scales actually quite quickly in the atmosphere. In the ocean we have to see. We definitely need more observation in the ocean as well, but I didn't touch on that. There's a whole range of, if you like, associated activities also on the WMO level, how we can improve the initialization of our models with a better coverage for these kind of high-resolution models in order to increase, if you like, the availability of observations, both in the ocean, the atmosphere, but also thinking about like how we can use hydrology observations in the context of like improving the downstream applications, because you could in principle, you know, think, we do this actually already, we assess the quality of our surface model with respect to the hydrology observations which measure at the end, which is currently, there's a lot of calibration going on, but we want to more intimately connect them, have like a, you know, we have scores for 500 geopotential height in the atmosphere, but in the future you could think of a score like for, you know, in the stratosphere, for sudden stratospheric warmings, and in the surface for the quality of like the river flooding or something like this.
Okay, thank you very much. Unfortunately, I think we're out of time for your question, but you can maybe find Nils offline and ask the question down. So join me, thank Nils again for this great talk.
Thank you.